Hello, grade 11s, and welcome back to another video on acids and bases. So in the last two videos, we looked at an introduction to acids and bases. We also looked at, within that particular introduction, we defined what acids and bases are according to the Arrhenius theory. We defined what acids and bases are according to the Lowry-Bronsted or the Bronsted-Lowry theory, however you wish to pronounce it, really doesn't matter, you know. And we've defined what we call in the second video, we actually defined what we call emphalites, what we call monoprotic acid. That was actually in the first video. We've defined conjugate acid base pairs, and we've looked at a lot of things, right? And in this video, I just want to talk to you guys about what we call protolytic reactions, right? So today I just want us to look at what we call protolytic reactions. Protolytic reactions. You know, you might find that probably in one of the textbooks you guys used, or you guys use in class, or maybe how your teacher would say it might be different from the way I say it. Maybe they might say it's they call them acid-base reactions, you know. But I prefer to just call them protolytic acids, as I have already, right? Cool. So we look at protolytic acids reactions today, right? And we look, or some might say, acid-base reactions. Cool. So what are protolytic reactions, right? So by definition, protolytic reactions are basically just reactions that that look at what, or rather that look at the transference of protons, right? So in proper English, you could say these are reactions, right? So these are basically just reactions during which protons are transferred, during which protons, remember what are protons? H plus, during which protons are okay, it's very bad handwriting. Okay, let's see. During which protons are I write really quick. I think that's probably why I write so unneat and unlegibly. Okay, so we look at protolytic reactions. We say that protolytic reactions are reactions during which protons are basically transferred. And this is how basically a structure, different, because we have different types of protolytic reactions, right? I think for grade 11, you guys are restricted to only 4, right? So which 4 are those? So we have the first one. I think it's best if I just number these, right? We have what we call an acid plus a metal, right? To give us a salt plus hydrogen, but not just any hydrogen, but hydrogen gas, which is just H2, you know? Okay. That's why I actually choose to not call these acid-base reactions, because it's not everything an acid reacting with a base, you know? I just prefer to just call them protolytic reactions. I'm not saying if your teacher decides to call it in a different way, that's also fine. I'm not saying they're wrong and I'm right. Okay. So we look at acid plus a metal gives us a salt plus a hydrogen gas. And then we would look at an acid, sorry, an acid plus a metal hydroxide. An acid plus a metal hydroxide. In this particular case, this would most of the time just be a base, right? So an acid plus a metal hydroxide still gives us a salt, but not just a salt, but it gives us a salt and water, H2O, right? What's the third one? Okay, then here we look at an acid plus a metal oxide, And what do these actually give me? This gives me a salt plus water. And then the fourth one would be an acid plus I think it's a metal carbonate. Yes. It's an acid plus a metal carbonate. And you guess what the product would be? Yes, a salt plus water plus CO2. Cool. So these are all the reactions that you have under protolytic reactions. So these are all the protolytic reactions that you are actually supposed to know, because you know what usually happens in the exam is that the teacher doesn't actually give you these things. What she actually gives you is probably the reactants, and you're supposed to actually figure out what your products will be, right? So let's look at the first reaction, reaction one. All right, let's look at reaction one. So reaction one is basically an acid plus a metal to give us a salt and hydrogen gas. Okay, so let's take a typical example. Let's say we have, just think of an acid. Let's take hydrogen sulfate or sulfuric acid. You know, it really doesn't matter how you call it. So we take a strong acid, which is H2SO4, and we react it with a metal. Remember, according to the equation, we are reacting it with a metal. What could that metal be? It could be anything. It could be, think of your metals. It could be sodium, it could be potassium, it could be lithium, magnesium, calcium, any metal, any group 1 or group 2 metal, you know. So let's take a look at potassium. Let's just say react with potassium. And you know that potassium is a metal, so expecting a solid, and expecting this to be in aqueous form. This is soluble, by the way. And what is then form? This will then form a salt plus a hydrogen gas. Now, I just want to give you guys a little quick hint. I mean, or rather, not just a hint, but just a trick that you guys can use, right? So you notice something. You then ask yourself, what would be the product that I form, right? So look at something. So I have H2SO4 plus potassium. What will be my product? If I know that if obviously you would know that you're supposed to end up with a salt, some particular salt with hydrogen gas, you can then just say plus hydrogen gas, you know? And then you would be like, okay, cool. What then would be my salt? Now you'd notice you have already taken this guy here, H2. Therefore, it would be kind of easy with this one to just conclude that your salt would be KSO4, right? But this is not correct. No, it is correct, but it's partially correct. It's not complete. Remember, potassium is a group 1 metal, right? And we know that it has a charge. The cation of potassium is K plus, right? And SO4 is a polyatomic ion with a charge of 2 minus. So notice something. Remember in grade 10. So if I take K plus and I take SO4 2 minus and I bring them together, what do I form? So remember, this guy here will just be the subscript for K, and then the subscript for K becomes a subscript for SO4. I think the use of the same color just becomes a huge mess. I think we should just use different colors. Okay, so how do we have? So we would have K, so we have SO4 2 minus plus K plus. And then we say the subscript for this guy here, sorry, the charge will become the subscript for K, and then this guy will become a subscript for K for SO4. So what is our resulting product? SO4, sorry, not just SO4, our resulting product will then be K2SO4, right? So that's what I actually had to have here. I hope you guys actually know that we're supposed to disregard. You can't have something like K2 minus SO4. That is so incorrect. So you just need to make sure that you just do not include the negative sign. Okay. Cool. So that's our salt, K2SO4. But then is our equation balanced? So let's see. So we notice that we have H2SO4 plus potassium to give us potassium sulfate plus water. How many potassiums do we have on the product side? We have 2 on the reactant. We have 1. So at this we can just put a 2 right there. Is this balanced? So let's see. We have 2 hydrogens, 1 sulfur, 1 sulfur, 4 oxygens and 4 oxygens, 2 potassiums and 2. Okay, now this is balanced, right? So this is our first reaction, an example of our first reaction. So what do we have? So let's look at the structure. The structure was supposed to be we had to have a certain acid plus a metal to give us a salt and a hydrogen gas. So let's look at it. We have our acid, H2SO4, plus our salt, our metal, which is 2K, potassium, to give us what? Our salt. So in this particular case, this was our salt, this was H2, this was our metal, and this guy right here, just gonna get him out of the way and then just try to make him a bit smaller. Yes, just put him right there. Okay, and then we have our acid. Cool, right? Okay, let's take a different example. Let's take nitric acid, right? Let's say this is nitric acid, HNO3, which is also very soluble. And then we react it with let's think of a different metal. Say magnesium, right? Magnesium, and then we say that gives us we should know that we're going to have our H2 as our final result. But what then will be our salt? Now we go again. So I notice that I would have my nitric acid, my H2, my nitric acid, reacting with magnesium, right? So it's reacting with magnesium to give us our salt and a hydrogen gas. Now, what exactly would actually be our salt, right? So what exactly would be our salt? Right. So I know that I have used my H, right? It's right there. So I know I'm left with just NO3 and magnesium. So I'm going to have magnesium NO3. I'm assuming you guys can actually see that there's a problem here. There's something incorrect here. Ah, you got it actually. So what seems to be our little problem here? I don't know what's wrong with this. Oh, yes, that's why. So the problem that we have here is with magnesium nitrate. Now remember, magnesium is a group 2 metal, so it has Mg2 plus, and you're going to react it with nitrate ion. A nitrate ion is a polyatomic ion. Now remember the rule. This guy here becomes a subscript for him, and he becomes a subscript for him. Now remember, we do not add the negative sign. So what is our resulting product? Our resulting product would then be magnesium. Remember, there's actually a 1 as a subscript right there, but we just don't write it. It's just not necessary. So you have magnesium nitrate. But remember, there's a 2 for the subscript. So I have to put these in brackets and then have our 2 there. Because, I mean, if it already has a subscript 3, and it just wouldn't make sense to just have it like this. You know, it's just a mess, right? So just decide to just add it and close the nitrate ion in brackets and then give it 2 right there, right? So that's what I actually need to have here. So that was our problem. So we're going to have it as magnesium nitrate. There we go. Okay, now we are fine. Now everything was correct. Or is it? Ooh, let's see. So how many magnesiums do I have on my reactant side? I have 1. And how many do I have on my product side? I also have 1, right? Oof, that was my bad. Okay, so my magnesiums are fine. But how many hydrogens do I have on the product? We have 2. And on the reactant, we have 2. I mean, this is as easy as just placing a 2 right there. But remember, that 2 also affects my nitrates, my nitrate ion, right? So how many nitrate ions do I basically have? I basically have 2 nitrate ions. Remember, it's 2 NO3 minus. And how many do I have here? 2 NO3 minus. So yes, my nitrates are actually balanced. Now my reaction is balanced, right? So what have you seen? We've identified that the nitric acid in this particular case will be our acid, right? This will then be our metal. This will then be our salt. And, well, hydrogen gas will be our hydrogen gas. And just write it in full. Hydrogen gas. Okay, hydrogen gas. Cool. So this is a typical example of, or examples of the first reaction. What was the first reaction? We take an acid, react it with the metal, we result in a salt and hydrogen gas, right? So this is what happens with the second one. So looking at reaction 2. Reaction 2. So what exactly would be the trick with the first one? What you need to know is that if you are given an acid, or you identify a particular substance as an acid, and you see that, okay, this acid is reacted with some metal, you should know that your end result, or rather your product, must be hydrogen gas and some particular salt. And then once you've identified that, you should make sure that your equation is balanced. And you also need to make sure that your equation has the correct, obviously, stoichiometric ratios. We're talking about balancing the reaction, right? And also that it's written correctly. You know, with situations like K2SO4, situations like magnesium nitrate, you know, it is very, very important. Yeah. So what does reaction 2 say? Reaction 2 says I need to have my acid, my metal hydroxide, and to give me my salt and my hydrogen. So I need to have my acid, my metal hydroxide to give me my salt and water. So that's what happens. So just a different acid. I think I've been using H2SO4. Let's take a different acid. Let's take think of an acid. Promise I can't think of an acid right now. Okay. Right. So let's take hydrochloric acid, right? And let's take hydrochloric acid and actually just react hydrochloric acid with a metal hydroxide. Now, what exactly is a metal hydroxide? A metal hydroxide, remember, what is a hydroxide ion? Let's actually start there. OH minus is our hydroxide ion. So a metal hydroxide would be any metal bonded to the OH minus, right? So we would have anything, Mg, and this guy right here, sorry, magnesium plus the OH minus would give us magnesium hydroxide, right? This is a metal hydroxide, right? So which one is our metal? Magnesium. And which one is our hydroxide? Well, OH minus, metal hydroxide. Or perhaps you could have potassium hydroxide. Remember, which one is our metal? Potassium. Which one is our hydroxide? Well, the hydroxide ion. So that's what they talk about when they talk about a metal hydroxide, right? So in this particular case, let's think of a random metal hydroxide. Let's take but let's take beryllium hydroxide, right? So we have Be, beryllium hydroxide. Now, if you're probably wondering, right, it's BeOH2 minus. Remember, OH minus is the hydroxide ion. Beryllium is a group 2 metal, so it has 2 plus. And then remember, this goes down there, and this guy comes right there, right? It's just that rule that you guys learned in grade 10. Cool. So we have hydrochloric acid plus beryllium hydroxide to give us just aqueous. And then we have this as aqueous. Right. So what does this actually give us? Now, this is where I want you guys to have your utmost focus. Right? So look at something. So I have my hydrochloric acid and my beryllium hydroxide. What exactly am I supposed to produce? So according to this, I'm supposed to produce my salt and water, right? We're looking at reaction 2. Supposed to give rise to my salt. Oh, this is bad. Let's make it white. My salt. Oh, this is even worse. Damn. Let's take pink. Ugh. Okay, you know what? We're gonna have our salt and our water, right? Okay. So what do we actually have? So we're supposed to have our salt and water. So how I actually used to remember this was to say, so if I'm gonna form my salt, then my salt must be a metal and some non-metal. Okay, that's how I used to remember it. So I used to say, okay, if I have to form my salt must be some metal and some non-metal, right? So look at this. And the rule of thumb would be, it's not really the rule of, it actually is the rule of thumb. What would you actually do? So what would actually happen is that you would try to manipulate this in this way. In the first substance, which is this guy right here, and the second substance. In the first substance, you take the first guy and you combine him with the last guy. Ugh, that's a lot of guys. What are you talking about? I take the first guy in the first reaction. What's the first element, rather? What's the first element in the first reaction? Hydrogen, right? So I will take hydrogen and bond him with the final substance, or rather the final, remember, so beryllium hydroxide is basically just beryllium plus OH minus, right? This is how it is right here. And then here it's just going to be my H plus my Cl minus. I really want you guys to give me your utmost focus. I would have this here, right? So in this particular case, what am I actually talking about? I am saying this guy here, the hydrogen, you notice that hydrogen comes first in HCl, right? So I'm going to take hydrogen as it comes first in HCl, and I'm going to put him together with whatever comes last in the second substance, right? So what do I mean? I'm talking about OH minus. So I'm going to take H plus and I'm going to put him together with OH minus. So that's how we form our water molecule. So we're going to have plus water, right? We'll get to the balancing at the end. Now I'm fine. What then do I need to do? I then say, okay, whatever remains will then be put together, meaning I have my Cl minus put together with my Be2 plus. Oof, I forgot my plus there. Okay, so how does that actually form? It actually gives me my salt. What is my salt in this case? Beryllium chloride. You guys actually see what actually goes on. And you're probably wondering, how did I get to BeCl2? Remember the rule. Be has a charge of 2 plus, chlorine has a charge of 1 minus, so the charge becomes a subscript of the other, and all that nitty-gritty knowledge you guys need to know. Okay, right. So we have formed our water and our beryllium chloride, which actually becomes our salt. But what actually needs to happen? Is this complete? Is it fine? So let's see. So I have, how many hydrogen atoms do I have on the product side? I have 2. And how many do I have on the reactant side? I have 1. So, oh, no, I actually don't have 1. Let's see. Remember, beryllium hydroxide is BeOH minus, sorry, OH2. So how many hydrogens do I actually have? Remember, I have 1 here and 1 here. So I basically have H2 plus the 1 there. So that gives me 3 H's on the product side. So how many do I have on the reactant side? I only have 2. Ooh, so I have 2 H's. So what does this actually tell me? So that tells me that a little bit of equation balancing knowledge would need to come into play, right? So let's see. How many hydrogens do we have here? We have 1, chlorines and beryllium and oxygen, right? Just going to do a little bit of equation balancing here. Okay. So hydrogen, chlorine, beryllium, oxygen. Remember the rule of thumb. Oxygen is always balanced at the end. So I have my hydrogen here and I only have 1, right? How many chlorines do I have? Exactly 1. Beryllium's 1. Oxygen's is 2. In fact, H here is supposed to be just 2. How many hydrogens do I have on this side? No, wait. Yes, it's 2 plus 1. So sorry. It's actually 3. Remember, the 1 here and the 2 here, right? So that gives us 3. And then how many hydrogens do we have on the reactant side? We have 2. Chloride ions, we have 2. How many berylliums? We have 1. And oxygens, we actually have 1. So now we need to start balancing. So we'd notice that for chlorine on the product side, on the reactant side, I need to actually just multiply it by 2, right? So it can be 2. So I know I have to place my 2 right there. But remember, the 2 also affects the hydrogen, so I had to say times 2 as well. So that gives me 6. That gives me 2. My beryllium is still 1. My oxygen is still 1. I mean 2. Okay. Now, is everything fine? No. So you notice that my hydrogens on the product side is 2. So I just need to multiply that by 3 to get my 6. Just a 3 there. My chlorines are fine. My beryllium is fine, right? Then what happens to my oxygen? It also gets multiplied by a 3. So how many oxygens do I have now? 3. How many do I have here? 2. Now we have a huge problem. So let's see what actually happens. So we're going to say beryllium hydroxide. Okay, so beryllium, 1, 1. So everything's fine except for the oxygen. Yeah, my chlorine, beryllium, and oxygen. Now remember, I have 2 hydrogens, right? So it's a hydrogen before the plus side and after. So it's just going to say H plus H, right? And then we're going to have the product side, product solid, hydrogen, chlorine, beryllium, and oxygen. Cool. So what do we actually see here? So how many hydrogens do we have on this side? So here on this side, by the HCl, I only have 1, and then by the beryllium hydroxide, I have 2. How many chlorines do I have? 1, beryllium 1, oxygen 2. How many hydrogens on this side? I have 2. And on this one, chlorine, I have 2 chlorines, beryllium 1, oxygen 1. So my goal is to balance. Remember, the rule of thumb, always balance oxygen at the end. I mean, most of the time, oxygen just balances itself. So what do we have? So I can multiply here by 2, and then I could get my 2 right there. Notice that it also affects my chlorine. Now my chlorine has 2. My hydrogen has 2 plus 2 to give me 4. And then here I'll just multiply that by 2 so I can get my 4. So our hydrogens are actually balanced, right? As well as our chlorines. So I just need to put a 2 right there. Remember, the 2 actually affects the oxygen in the water molecule, right? So now we have 2 water molecules, right? But we have 4 hydrogens and we have 2 oxygens. So let's just multiply that by 2, and that gives us 2. And think everything else is actually fine. Remember, you see what I mean when I say oxygen actually balances itself? Now we have our balanced equation. So if you guys still have a problem with knowing how to balance equations, I should actually if you guys actually need help with that, then you can just drop that in the comment section, or you can just look at the grade 10 video on balancing chemical equations, because there's also that for grade 10s, which you should have learned in grade 10 or 9 or 8, I'm assuming it should have been in 8. Okay, now we have our balanced equations. So what can we see here? And then notice that we have HCl, which is our acid. We have beryllium hydroxide, which is our metal hydroxide. And we have beryllium chloride, which in this case becomes our salt. And we have that, which becomes, well, our water, which follows that structure that they gave you right there. An acid plus a metal hydroxide to give you salt and water. Acid plus metal hydroxide, salt and water, right? Should be very easy. So let's take a different example. Let's take, what did I just do? Look what you made me do. Okay, so let's look at this one. So let's take H2SO4, right? And we react this guy with magnesium hydroxide this time. Magnesium hydroxide. What does this actually give me? Now remember the trick. Remember the trick. So I have 2H plus, right? With SO4, 2 minus, plus Mg, 2 plus, with OH minus, 2 of that. So what happens? Remember, the first guy with the last guy on the other side, and so on and so on. Meaning, this guy here will then form something with him. Remember, the first guy in the first substance forms a pair, or rather a certain type of, just call it a relationship, right? So the first guy in the first substance forms a relationship with the guy with the final guy in the last substance, right? So let's see, just to clear the confusion. I mean, you can just remember it in your own way, right? So this guy here will become friends with this guy right here, right? So first goes with last. and then second goes with first, meaning that this guy here will go with this guy here, right? Second with last, sorry, first with last, second with first. Yeah, I think that's actually a nice way of remembering it. Okay, so sometimes it's really fun to just form like a person, your own mnemonic, think about it. So it's first with last, second with first. FLSF. What mnemonic could you form here? Friends like such food. Friends like soft food, or friends like silly friends. I don't really know. You could just form your own personal mnemonic. Trust me, it really helps from time to time. I just never did that, but it could work for you. Okay, cool. So what then should we actually form? We do know that we should form our water, right? There we go. So we are supposed to actually form our water. Okay, so we're supposed to form our water, right? Now, what then will be our salt? Remember, second with first. First with last, right? And then second with first. I really do hope you guys are actually seeing how this actually works. We're not the same as people, so we would obviously have different ways of grasping something. So we have magnesium. Oh, actually, no brackets needed here, so it's just magnesium sulfate. Right. Okay. So we have magnesium sulfate. Now let's see, is our equation balanced? So we have two hydrogens here. We have two hydrogens here, and here we actually also have two. Here we only have two. So this gives me a total of 4. So I just need to multiply this guy. We can probably, wait, is it actually balanced? Let's see. Yes, here we have 4. We also need to get 4 here, so we can just multiply that by 2, meaning I can just place my 2 right there. Great. I think now it's balanced. Yes, it actually is. Okay, so which reaction have we looked at? We've looked at the second reaction, right? So this is the second reaction that we've actually looked at, right? Okay, so what does the third one say? We say we are talking about an acid plus a metal oxide to give us a salt plus water. So let's see. This is reaction 3. Reaction 3. It's an acid plus a metal oxide to give us a salt and water. I think I'm just going to rewrite this. It's an acid plus a metal oxide plus a metal oxide to give us a salt plus water. Is it actually water? Yes, it is. Yes, it is. Yes, it is. Okay, so what do we then have? So let's take our acid again. So just think of an acid. What's my favorite acid? Okay, so if you look at an acid like here, our favorite friend here, HCl plus a metal oxide. Remember, if a metal hydroxide is a metal and hydroxide ion, that means a metal oxide will be a metal bonded with oxygen ion, right? Cool. So a metal oxide can be anything. So in this case, we can use, I don't know. What do you guys actually want to use? Magnesium oxide? I really don't know why I always use magnesium. It's supposed to be magnesium oxide. What does that give me? Now remember, first with last, second with first. First with last, second with first. So we have first with last, second with first, right? So let's see what happens. So if I know that I need to form my water, right? So what will I have? I'll then have plus water. Now we use first with last, second with first. So second is chlorine, was my first magnesium. Therefore, I get magnesium chloride, right? Cool. And is our equation balanced? Let's see. So how many hydrogens do I have? I have 1 and I need 2, so I can just put a 2 right there. my oxygen's balanced? Yes. So that is our fully balanced equation. Right. So this is what they mean when they say, so what do we identify? We identify this guy as our acid, this guy as our metal oxide, this guy as our salt, and him as our water, H2O, right? Cool. Really hoping you guys are just seeing these things and how it actually works. I mean, if you had to do the same thing, maybe with a different element, right? So it would be some particular element, I'm sorry, not element, but acid, maybe nitric acid or sulfuric acid or, any acid that of your own choosing, right? So for the purpose of the length of the video, I'm not trying to just dwell much on things that I'm really hoping you guys are getting right now. So the last one says an acid plus a metal carbonate gives us a salt, a water, and a carbon dioxide, right? So we have reaction 4, reaction 4, reaction 4. So reaction says we need to have an acid reacting with a metal carbonate, a metal carbonate to give us a salt, water, and a carbon dioxide, right? So, what is a metal carbonate? I mean, if a metal hydroxide is a metal and some and is any metal with hydroxide ion, if a metal oxide is any metal with an oxide ion, then a metal carbonate will be any metal with a carbonate ion, right? Cool. So we would have an acid. So let's say we take our acid HCl. I probably might need to use a different one. Nitric acid. Jesus Christ, I've been using HCl. Okay. A nitric acid reacting with a metal carbonate. So what metal carbonate can you think of? Let's say calcium carbonate, right? Calcium carbonate. Right. So calcium carbonate. So we actually know that we are supposed to end up with our salt, water, and carbon dioxide, right? So we know that we should have water plus CO2. Now, what then will be our salt? Remember, first with last, second with first. First with last, second with first. So we have first, which is hydrogen, with last, which will then be CO3. I'm actually going to show you how this boils down to CO2 and water, right? And then we would have calcium with our nitrate ion. So we'd have calcium, nitrate, bam. There we go. First with last, second with first. I really hope you guys are actually seeing how this works. This is very fun. Okay. Now, what then would happen? So how exactly did we move from hydrogen to carbon dioxide? So I then say I'm going to give you HCO3, right? But remember that this should be H2CO3. This breaks down. When it decomposes, it then becomes H2 plus. Right, so when it decomposes, so when a hydrogen carbonate, right? A hydrogen carbonate, when it decomposes, in fact, this should be a reversible reaction now that I think of it. This should just use these arrows, right? So when it decomposes, it forms H2O plus CO2, right? Okay, so that's H2O plus CO2. So how many hydrogens do I have here? I have 2. I also have 2. How many oxygens? That's 1 plus 2, that's 3, and 1 carbon. So this is how, right? I just did this just so I can show you how our first with last, second with first works. So we know that our first, which is hydrogen, must go with last, which is the carbonate ion, right? So we're going to have HCO3, 2 minus. Remember, this guy becomes a subscript right there. So we're going to have H2CO3, which then breaks down into these substances. Hence, you have that right there. Okay. I'm just trying to show you how the first with the last, second with first actually works. I really really enjoyed questions that actually had me having to use that rule, you know. So let's take a different example. So let's take, oh, I'm sorry for the high pitched voice. Let's take HCl and react HCl with, oh, sorry, there's a 3 missing there. Strontium carbonate. Okay. So what actually happens? So we have strontium carbonate, and what is our result? H2O plus CO2. Where does these guys come from? They come from H and CO3, right? Okay. So let's see if it works. So we have first with last, bing, 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 gives us water and CO2, right? Okay, so what happens with second and first? So it's first with last, second with first. So we have second with first, which then gives us strontium chloride, SrCl2. Okay, there we go. So we have SrCl2. So is our equation actually balanced? In fact, was the first one actually balanced? I feel like we didn't look at that one. Let's see. So how many hydrogens do I have on my product? I have 1, and on my reactant I have 2. Ooh, so it wasn't, and we actually left it. Oh my gosh. So we need 2 here. So we need to also have 2 nitrates, which we actually do. 1 carbonate, 1 calcium, sorry. So 1 calcium. How many oxygens? So I have 3 plus 3, that's 6, right? And then the product side, I have 2 plus 3 times 2 is 6 plus 2, and that gives me 8. So this one is actually not balanced. We actually need to balance it. Oof, and I actually left it. Oh, so sorry. Okay, so let's balance. So how do we look at? So now that we have placed our 2 here, remember it affects the oxygen. So I have oxygen 6, the 6 is from this nitric acid, plus the 3 there, and that gives me 9. And then how many do I have here? So from this guy here, I have 3 times 2, which oxygen gives me 6, plus 2, plus the 1, which gives me 3, which is 9. Okay, the oxygens are actually balanced, right? What else do we actually need to look at? Yeah, actually, our reaction is now balanced. Let's see, nitrates, calcium carbonate, carbons, I have 1. Okay, cool. Yes, it is actually balanced. Right, so let's see if I can actually balance this one. So how many hydrogens do I have? I have 1 here and I have 2 there, so I can just put my stoichiometric 2 right there. Right there. Yeah. And just by the looks of it, everything else seems fine. Okay, now what have we done? We have looked at all the different types of reactions, all the 4 protolytic reactions, right? What are protolytic reactions? Those are reactions during which protons are transferred. Yeah, right? Now remember the rule of thumb. Just have fun with it, you know, just do different types of examples and actually see if it works. Remember, last with first. Sorry. First with last, second with first. So this works usually. So with first, I'm having nitric acid and calcium carbonate. So my first would be the first in the first substance. The last would be the last in the second substance. So first in this guy here, who's the first in HCl? H. Who's the last in SrCO3? It's a CO3. So they come together, right? And then we have second with first. So how does that one work? So second with first means second in this one is who? Who's second in the first one? Chlorine. And who does chlorine bond with? The first one in the last one, which is strontium. That's how we have SrCl2. So that's how it actually works. It's really fun. But if you guys actually feel like, okay, you could remember it in a different way, then that's also fine. Okay, cool. So just a quick thing before I end off the video. So I just want us to look at also what we call um indicators, right? I want us to look at what we call indicators. Okay, so I just want us to look at indicators and how it actually works, right? So with indicators, right, we have different types of indicators, right? First, let's start with defining what an acid-base indicator is. So an acid-base indicator, just gonna say it, and I'm not sure if you guys are gonna write it down. So an acid-base indicator is basically some chemical, right? An indicator is a chemical, right, that changes color depending on the alkalinity or the acidity of a substance, right? Or rather of a solution. When I talk alkalinity, remember when I say something is alkalinic, I'm basically saying it's a base, right? So an indicator is a chemical that changes color depending on the acidity or the alkalinity of a certain solution. So depending on how acidic or basic a solution is, right? So we look at two things. Is that particular solution a weak base? Is it either a weak base or, is that particular solution a weak acid or a weak base, right? So that's what we look at. And we would actually say, well, that particular indicator, so it changes color. So the indicator changes color, right? Ooh. There's really a very huge fight about how the word color is spelled. So it changes color due to, you know, it changes color. Jesus Christ. It changes color when what actually happens. So it changes, so a certain indicator will change color when it reacts with some H plus, right? So the color would change due to some reaction with H plus, due to some reaction with a proton, with H plus, right? Or with an OH minus ion, right? And obviously this would talk about a base, and this guy would talk about an acid. Okay. I'm so sorry for the terrible handwriting. Cool. So now what then do we look at? We look at indicators as weak acids, right? An indicator as a weak acid. Cool. So we look at an indicator as a weak acid. So what do we do? So this is how it actually works. If an indicator is weak, right? If an indicator that you have is weak, then you can write it in this form. This is just it's not how you would have to write it in the exam, but it's like a certain structure you would follow. So you would have your H, I, N. IN just stands for the indicator, which will then give us H plus, which is our ion, and our IN minus, which is our base. Okay. Okay, so what is the main idea behind this? So what is the main thing we should focus on? So what you would see here is that my reactant side, which is this guy right here, my reactant side is in an acidic form. It's in an acidic form, right? So my reactant side is in an acidic form, and it has a certain color. So it has a color, right? It has some color that it has. So it's only one color that it has, right? Cool. And then what happens with the IN minus? This guy is in basic form, right? And we wouldn't obviously expect the basic form to have the same color as the acidic form, right? So we should know that this should be in a different color, different color. Okay, so we have the acidic form, which is this guy right here, and the basic form, which is this guy right here. So this guy's color would be different from his color. So what you would see, an indicator is a certain, so you'd see maybe on an indicator, maybe in the exam, they might give you a certain indicator. And a certain indicator changes color depending on how acidic or basic a certain substance is. So that's when we also look at pH, right? Cool. So HIN is our acid form of any substance, a substance in acid form. And then the IN minus would be that particular substance in a basic form, right? And the color would be different. Now we talk about equilibrium, right? And we say, if an acid solution, right? So I'm just going to make an asterisk. If an acid solution has more H plus or a high concentration, if an acid solution has a lot of H plus, a lot of this guy here, a lot of this guy here, what do you notice? Notice that H plus is on the product side, meaning it's on the right side, right? So it's on the right side. But what happens? So when you talk about equilibrium, equilibrium in a way is to say, what happened? I have more H plus, which is a product. Equilibrium says, I do not want you to disturb my equilibrium. So I will try to reinstate equilibrium by favoring the reverse reaction, right? So just don't think too much about that. Just trying to make you understand this. So I say, if I have a lot of H plus or a high concentration of H plus, that means I have more products than reactants. So what does equilibrium say? Equilibrium then says, I want to reinstate equilibrium by opposing your change. What was my change? To have more H plus. So how does it oppose that? It makes the reaction have less H plus by favoring the reverse reaction, right? So it favors the reverse reaction, meaning equilibrium shifts to the left, right? So if it shifts to the left, you notice something. This guy here then gets the upper hand, right? He will start to dominate. Now, the color that you are expecting to see as a result would be the color of this guy here, right? The color of HIN, right? Because after equilibrium has been reached, he became more dominant because his reaction was favored, which was the reverse, or rather the left reaction, right? But you notice something. If I have less, I'm just going to try to erase these, just really, really becomes a mess. So, okay. So if I have less H plus, right? I have less H plus, less H plus. What does that mean? It means that equilibrium will then say, if I have less H plus, I want to reinstate equilibrium by having more H plus, meaning I will then decrease this guy. So not really. Now I'm just going to grade 12 content. So for equilibrium, I will then favor the forward reaction, the right reaction. Why? Because I have less H plus initially, and I want to have more H plus. How can I have more H plus? By continuing to favor the forward reaction so that more and more and more H plus can be formed. Now notice something. This is also a product. So if I have my forward reaction favored, I increase the concentration of my H plus as well as the concentration of my AN minus, which is really, remember, the basic form, right? Meaning, as a result, my resulting color would be a color of this particular base, right? So I said this base was had a certain color, let's say orange, and then my resulting color would then take favor of the orange color, which is the color of the base, because there's more base than acid, right? So the pH is rather way higher than, well, greater than 7. You know, we know anything greater than 7 as a pH on the pH scale is basic, you know. So we would have more In minus than HIN, right? So we would take preference of this guy's color, right? That is when we have less H plus. What happens? I want to favor the forward reaction so that I can have more H plus. But notice H plus and In minus are both products. So if I have H plus, I increase my H plus. I'll then say H plus. I also increase In minus, meaning I'm increasing base. So I'm increasing the power. Base becomes more dominant. Meaning if it becomes more dominant, then the color of the base will then dominate, right? Cool. And you know, just a typical example of an indicator for this particular situation would be what we call, please pardon my spelling, phenolphthalein. Not sure if I spelled it right. Phenolphthalein. Yeah. Okay. Phenolphthalein. It should be correct. I'm not sure really. Okay. So what happens with phenolphthalein? What are the changes? So with phenolphthalein, this is what happens. So with phenolphthalein, if it happens that you form an acid, then what happens? You have colorless. In fact, let me just write it like this. So if an acid forms, phenolphthalein becomes colorless. But if you have a base formed, phenolphthalein becomes pink. And the pH of phenolphthalein, usually that would just happen when it's at a pH of 8 to 10, I think. Okay. So when an acid forms, phenolphthalein is an indicator, by the way. So I think I should just write phenolphthalein indicator. So phenolphthalein indicator becomes colorless when an acid is formed, and it becomes pink when a base is formed. And that's usually just by when it gets at a pH of 8 to 10. Cool. Okay. Now we look at indicators as weak bases. I know this might be quite a lot to take in, you know, just give it some practice, you know. And if you need more explanation, then do email me on my email and I will get back to you real quick. Okay. I would have shot my contact details, but hey, this is South Africa, man. You really wouldn't know what happens. Okay, so we have indicators as weak bases, right? So how does it happen? So the general structure would be, I would have my B, which would represent a base, plus, sorry, not plus, wait, so I would have my B, which would represent a base, plus my H plus, to give me my BH plus, right? So this is, the B is our base, the H plus is our, I mean the B is the base, the BH plus would be the acid. So we have this is the what? Acid form. And this guy right here would be our base form. Okay, cool. So what happens? If it happens that I have more H plus, right? So if I have more H plus, what happens? Remember, I have more H plus. So what does equilibrium say? Equilibrium then says, I have more H plus. I want to have less H plus. So what happens? I use the H plus that I have by favoring the forward reaction, meaning as I use H plus, it gets lesser and lesser and lesser. That's what equilibrium actually wants. So it says, I have more H plus and I want to have less H plus. So I can counteract that disturbance. So what does it do? It favors the forward reaction so that the H plus can decrease. and then it forms BH plus. So what are you expecting? So you're expecting H plus to decrease, as well as you're also expecting the B to decrease. Remember, the B is also a reactant, so B would also decrease. What would happen to BH plus? Remember, you favor the forward reaction, BH plus will then increase. So which direction is favored? The forward reaction is favored, right? That's how you lead to an increase in BH plus. The forward reaction is favored, right? The color you would expect to see is the color of this guy right here. Whatever the color of this guy is the color that you would actually see, right? You'd see the color of the acid, right? Cool. So applying the same logic. So think about it. Applying the same logic. Pretty sure you guys are starting to get how this actually works, right? So I'm just going to remove these and this guy right here. So what happens? If I have H plus and I have less H plus, what happens? Equilibrium says I want more H plus, meaning the reverse reaction would be favored, right? Now I have the reverse reaction being favored. I had less H plus in the beginning. Equilibrium says I want more. So H plus will then increase. B is also a reactant, so it increases. What happens to BH plus? We use it up and it basically decreases. So we are favoring the reverse reaction, right? So that's basically how it happens. So the resulting color would be the color of the base. So you would expect to see the color of the base. Okay. So what is that particular color? So when you have an acid forming, then your color would be yellow. That's where we're talking about a certain indicator. I think I should do what I did before. So we'd be talking an indicator that you would use here, which is called bromo. Oof, forgot the name of that indicator. Bromo. Ooh, bromothermal blue. Yes, bromothermal blue. So bromothermal blue basically gives us a yellow color when an acid forms, right? And it gives us a blue color when a base forms. And it gives us that particular color at a pH of 6 to 7.6. 6 to 7.6. Yeah. Okay. Cool. Right. So just a quick summary of the different types of indicators that you would have. So I'm just going to quickly make a young quick thing right here, right? So you would have your different indicators right there. And then you would have the certain color, it would be, cool. So you have your indicators here. Our indicators, the color of the acid, the color it changes to when it's more acidic, the color that it changes to when it's more basic, and at what pH does it actually happen. Cool. So the indicator is litmus. We have another one which is phenolphthalein. This name really becomes a problem. I have to write it down. Phenolphthalein. Bromothermal blue. Bromothermal blue. As well as, what's the final one? Methyl orange. A very common one is there as well. Methyl orange is like, it's very common, Oof. What's wrong with me in my handwriting today? Orange. Eyeball. Okay, let's try that one more time. Orange. There we go. So this is our acid color. So the color of litmus when a certain solution is more acidic, it turns red, right? And when a certain substance is more acidic, what does phenolphthalein turn into? It becomes colorless, remember. When it's acidic, phenolphthalein becomes colorless. And then what happens with bromothymol blue? When our substance is acidic, it turns yellow. Yes, yellow. And then what happens to the methyl orange? It becomes red, just like the litmus. So what happens when a solution is more basic? The litmus basically just turns blue. What happens to bromothymol blue? It turns blue, remember? And then what happens to phenolphthalein? It turns pink. And what happens to methyl orange? Methyl orange then turns yellow. Okay. At what pH would litmus actually have these? So it would be at a pH of 4.5 to 8.3. Phenolphthalein would be from 3.1 to 4.4. This guy would be from 8 to 10. Sorry, not phenolphthalein. I'm so sorry. I just remember that my phenolphthalein was just, we did it right here. So it's 8 to 10. Sorry. So phenolphthalein would be from 8 to 10, right? And our bromothymol blue would be from 6 to, why do I keep having it like that? Our bromothymol blue would be from 6 to 7.6, and methyl orange would be from 3.1 to 4.4. Okay, and that is it, right? Okay, so what do you actually need to know? You need to know that indicators are weak acids or bases, right? An indicator changes color depending on whether a substance is more basic or more acidic, or rather depending on the concentration of the H plus ion. Is it high? Is it low? And those particular things, right? And it also depends on whether, and you need to know, sorry, you also need to know that each indicator has two colors, right? Can be a different color when it's acidic and a certain color when it's basic. It can't have the same color for when it's acidic and basic. I mean, you really wouldn't know whether solution, I mean, that's basically why scientists would use an indicator to know whether a certain solution is acidic or basic. So if it's acidic, you're expecting to get a different color. So when phenolphthalein is acidic, when a certain solution is acidic, phenolphthalein is colorless. When a certain solution is basic, phenolphthalein is pink, right? And from this, you can basically just identify the pH of the solution. Usually in experiments in the lab, it just becomes easier for the scientists to actually determine the pH of a certain solution visually. Okay, now I think this concludes the session, and on the next one, we should be looking at different types of questions, from past papers, just to put acids and bases and everything we've covered into action, just see how everything is going, right? But anyway, from me to you, thank you for watching the video. See you again in the next one.